This is week 6, screencast 1 for Business Administration 571. There will be only 2 screencasts this week because it's an exam week. The exam opens up on Friday at 9 and closes Sunday at 1 minute before midnight. Before I move into something else, I wanted to finish up this idea of running a control chart on the number of units that are good in between bad units. And as long as that number stays big, you have good quality. And if it gets bigger, then you have even better quality. So there's no upper limit on the sensitivity of the chart to improvements in quality. And that's a big difference between a rare events chart, as they call it. It's actually a G chart, and an NP chart, which counts the number of bad units in a batch of size n. Of course, if you have really high quality, you might need a tremendously large batch size before you acquire any non-conforming units. So I've written a little program modified from an example in the SAS library, and let me open up this program. So out on the G drive, there's a file called rare chart. And rare chart, as you can see here, starts out with a data set on urinary tract infections. So this is a quality course, and where is quality used a tremendous amount? In the healthcare field. They've really taken it to heart, and they're using it from billing procedures for patients to office visits to handling procedures in an emergency room. Well, in hospitals, there is a big problem with infection, and at a particular hospital, they were concerned that there was a higher than normal incident of urinary tract infections among patients in this hospital. So somebody said, well, let's do a control chart on how many days that go by before we have one or more patients be diagnosed with urinary tract infections. Okay. So we're trying to clean up our literally our procedures so that the incident of these infections becomes extremely rare. We would like them to go to 0, but that's not at the moment feasible. So let's start seeing how we're doing by charting how many days go by before we see one or more urinary tract infections being reported. This is similar to the old standby of emphasizing safety in a industrial workplace, and you can see in many old factories paper charts sitting pinned up to the walls around the machines, loudly proclaiming that we have been 72 days without an accident. This goes back to World War II and earlier, where the insurance companies, of course, are very interested in big production lines getting their accident rates down, because the insurance companies then have to pay buckets of money in worker compensation. And so they have all these programs that are aimed at trying to make safety have a higher priority on production lines. And it was a big problem before OSHA. Workers were exposed to all sorts of bad stuff. They were required to engage in rather risky behavior around giant machinery, and there was a lot of death and injury. Things are a lot safer nowadays, although there's lots of grumbling about having to implement safety procedures. But for the most part, it's safer than it was, say, in the 1960s in most industrial and large machinery workplaces. Well, for this, a couple of cool things. We're going to input days between urinary tract infection. And so that's a proxy for how many patients over across the whole hospital are free of urinary tract infections. So days between infections. And then @ sign, and that means keep reading across a row this variable until you hit the end of a record, and then just keep going on to the next record. So you can just list them, and you don't even have to have the same number per row, and the idea is that each one is an observation. Now, we're not subgrouping here. This is kind of a nice thing about the G chart. There is no need to artificially create the size of a batch. So we're directly measuring how long a run we have before we have an event that is a failure of the process. So we don't like days between, so we multiply it by the number of minutes in a day to get minutes between. And now we're ready to run our pre-written SAS implementation of what's called a G chart, and they've chosen to call it rare events. Really clever. So here comes the data. Chart. Please give me a chart for minutes between, and put it all on one page. So let's see if we can run this puppy. And so we see that it has dutifully given us an upper probability limit and a lower probability limit. These would be viewed as control limits, and they have a false positive rate of 0.0082. So if we stray above the upper limit, we can say that the average time between infections, the average number of minutes between infections, that average time has gone up. So we've had a shift in the mean. That is cause for celebration, because the mean is an index which gets better as quality improves. If we stray below the lower one, then we can say that we have lost quality. Quality has gone down. The probability of having an infection has gone up. And notice that since the false positive rate is 0.82%, it's very low, and that explains why there is such a range in the limits. If you look at the data, though, there is some reason to believe that the variance of this variable is starting to increase. Okay, so I just wanted to make it clear that there is an existing SAS procedure which allows you to replace the NP chart with a chart that is better at monitoring increases in quality. Okay. So, the big scoop for today, though, is not rare charts. It's actually Six Sigma. So let's talk about Six Sigma. So this week's topic is 6 sigma. Management. The 6 sigma management system. So this is an invasive management system. This is designed specifically to rock the world of people, both employees in the firm and management of the firm. So 6 sigma I'm going to write as 6 sigma, just to be brief. The name means that a quality metric X will have specification limits and those are typically designated as upper spec limit, lower spec limit, such that the probability of a non-conforming unit every time you try to build a unit is less than 3.4 times 10 to the negative 6. Even when a 1.5 sigma mean shift has gone undetected. So, in words, what is being said is the production line is so good that the specification limits, having been given by engineering, are almost never exceeded. The only way you're going to do that is to arrange to have the mean and the variance such that the probability, assuming a normal distribution, the probability of making a non-conforming unit is around 3.4 times 10 to the negative 6. Or if you make 1,000,000 units, 3.4 of them are going to be bad, non-conforming. So how does this look? Well, I think that it's important to get a handle on what this definition means relative to what we've seen with the subject of control charts up to now. So here's X bars PDF on a X bar chart. Sigma, the variance of X is sigma squared. The mean of X is mu. Way out here is the lower spec limit, and way over here is the upper spec limit. Now the spec limits are not under the control of production. Six Sigma is all about the production activity. It's not about engineering. It's about actually making the device or providing the service that the firm is engaged in. But the spec limits come from the design of the machine or the design of the service. Well, what is under production's control? Under production control. Well, the variance and the mean. So we need to have the variance so tiny that it's going to take 12 standard deviations, 12 square roots of the variance, to make the journey from the lower spec limit up to the upper spec limit. So sigma better be pretty darn small if engineering has set the spec limits to be very narrow. And you're thinking, well, I know how to jimmy this setup. It'll be easy. I'll just make a lunch date with the manager of engineering, and I'll say, why don't you go ahead and set the spec limits so that they're really wide. That'll make it easy for us in production to do a little bit of work and get the variance of our production line down enough to where we will satisfy the definition of the Six Sigma process, and we can then boast on our website that we are, as it is called, Six Sigma conforming. So you've bought the manager of engineering a nice lunch, and you're proposing this idea, and you think, all I got to do is make this agreement with this person. The person says, well, we're making a supercharger for the Dodge Challenger. Now, in the world of sports cars, Dodge Challenger is actually a pretty cheap sports car. If you look at competing products out of Porsche, say. And Dodge now offers, as an option, anybody who has the money to have a supercharger bolted on the top of their engine. Well, this is a minor revolution in production, because there are two rotors that spin in such a way that this distance in between them is somewhere around 100 thousandths of an inch. Super tiny clearance, and this thing is spinning at around 9,000 RPM at higher speeds of the engine. It's belt driven. Well, it was not possible to put a supercharger into production until very recently because the tooling wasn't good enough. If these surfaces contact each other at speed, that supercharger will basically explode because you have so much energy, and these are rather large pieces of metal. So nobody dared offer a supercharger on a car because they knew that they couldn't hold the tolerances in a production setting and that they would have lots of failures until very recently. Now the tooling is really good. I bring this up because the spec limits, the difference between the upper and the lower spec limits, has got to be really tiny. So this manager that you've taken to lunch nicely says can't help you. You say, what do you mean can't help me? Can't help you because in order to make this machine work at all, we haven't set these spec limits for fun. We've set them because we know the spec limits on our drawings that we've given you to build are there because if they are exceeded, we know the machine will break. And it could break in a very catastrophic way. And so no way are you going to run production and ever make a unit outside these spec limits. If you do, you're going to throw that unit away. That's non-conforming. Do not bolt it to anybody's engine. So the spec limits are basically cast in cement. They're hardwired, one of the little phrases in the business world. You can't mess with them. The only two wiggle room things you have are the mean and the variance on your production line. To be Six Sigma conforming, basically the variance has to be incredibly small. Back to this picture. Here is the PDF of X. Now we know from the central limit theorem that sigma squared x bar equals sigma squared over n. That's why the density function of x bar is pinched relative to the density function of x because it has lower variance for any sample size bigger than 1. I mean subgroup size. In here, are our control limits. So this is the upper control limit, and this is the lower control limit. And so the point I'm trying to make is Six Sigma is not about X bar, because X bar is dependent upon the subgroup size you've chosen to run. Six Sigma is about the metric itself. If you're measuring a critical dimension and you're using that to build your X bar chart, Six Sigma comments on the mean and the variance of X itself, the raw variable you're measuring, not the subgroup mean. And Six Sigma's comment is, if you want to be able to say that you're Six Sigma conforming, so the phrase is Six Sigma conforming, a Six Sigma conforming process. If you want to be able to tout that on your website or mention that to potential customers for your products, hoping that you will be a favored supplier to some big outfit that is in a position to buy your unit that you're building, then you need to drive the variance down and get the mean in the right place so that it takes 12 production line process standard deviations to span the range between the lower and the upper spec limit, which you have no control over. So this is a way of putting a standard on how low the variance of a production line is. This has been taken over by many other fields, and like I said before, the health field has taken it to heart. And you now have various ways of talking about the quality of the delivery of a health product, and the infection rate in a hospital is just one of many examples. If you have driven the variance of infection, you're keeping track of how many infections are happening, say, per week. If that variance is driven to darn near zero, then you have a Six Sigma conforming process on the infection rate. Now the mean doesn't have to be zero. So Six Sigma is focused on the variance. So a lot of people say we need something that talks about the mean of the process, not just the variance. And that's really the motivation for lean Six Sigma. The word lean comes in basically to deal with the fact that the mean of a metric which is measuring scrap or cost, that mean needs to be driven to zero, just like the variance needs to be driven to zero. But this is an add-on to the classic Six Sigma philosophy. End of screencast.